want to review a couple other useful ideas about two-dimensional velocity and acceleration. Here's a useful idea. We know that we generally want to draw the path for any object. We want to draw the path of motion for the object. Well, the overall velocity vector is always tangent to the path. The velocity vector is tangent to the path. The velocity vector is tangent to your path. So let's say we have an object that's moving along this path. Here's the path that the object is moving along. Let's try drawing the velocity vector at this point. Try to draw the velocity vector at that point. Well, you can't really tell how long the velocity is, but you do know that you have to draw something that is tangent to this point. So I hope that you can see that I've drawn this vector as tangent to this point. Obviously, this would not be tangent. So this is not what we mean when we say tangent. This is not a tangent arrow. This is an arrow that's tangent to the curve at that point. So this would be the overall velocity vector at this point. How about at this point? Let's try drawing the overall velocity vector at this point. I hope you gave that a shot. Well, again, it should be tangent. Again, you don't really know how long this arrow is going to be, but you know that it's going to be pointing in this direction. So if you've drawn a shorter arrow or a longer arrow, that's fine. But it's got to be pointing in this direction, tangent to the curve. How about over here? Draw the velocity that is tangent over here. This is supposed to be the bottom of the path. Well, here's the velocity vector that's tangent to that. Try drawing the velocity vector over here. I hope you gave that a shot. Tangent to the path. We don't know how long it is, but we know it's tangent to the path. Okay, so the overall velocity vector is always tangent to the path. The overall velocity vector is always tangent to your path. That's worth making a note of and memorizing. The overall velocity vector is always tangent to your path. Now remember that the overall velocity vector isn't all that helpful. What would you do after you've drawn the overall velocity? After you've drawn the overall velocity, you would break it into components. Remember, overall vectors are not very useful. It's only the components that are useful. So once you have the overall vector, your next step would be to break it into components. For example, try breaking this vector into components. I hope you paused the video and tried that, breaking this vector into components. We have to draw a right triangle that uses this overall vector as its hypotenuse. Well, there we go. We'd have to draw arrows down and to the right, and this would be v sub x, and this would be v sub y for this velocity. So do the same deal over here. Break this into components. I hope you did that. We draw a right triangle that has this as its hypotenuse. Here's v sub x. Here's v sub y, and this is still pointing down and to the right. Now, technically, I really shouldn't be using the same symbols for both of these v sub x's, because there's no reason to think that they're both going to be equal to each other. So I'm going to be a little bit sloppy here. I'm going to use the same symbols because I'm being lazy, even though maybe I should call this v sub x1 for point 1, and this should be v sub x2 for point 2. But I'll be a little lazy and not do that here. What are the components of this vector? What are the components of this vector at the bottom? I hope you paused the video and gave that some thought. Well, this is a vector that only has a horizontal component. It's all horizontal. So we could say the overall vector is the same as its horizontal component, and we can say that for this vector, the vertical velocity is 0. For this vector, the vertical velocity is 0. There is no vertical component. It's all horizontal. All right, and finally, let's draw the components for this vector. Now, this has both a horizontal and a vertical. Again, really, I probably shouldn't be using the same symbols for this x velocity and for this x velocity, but I'll be lazy. This is pointing up and to the right, so the legs are pointing up and to the right. Okay, so if you have the path of an object, then you can draw the overall velocity vectors as tangent to the path. But the overall vectors are not very useful. The next step would be to break the vectors into components. It's components that are useful for solving problems. Overall vectors are not very helpful. Do you remember, what's your velocity when you change direction? What's your velocity when you change direction? This is something that we discussed, I think, in the first series of videos on general one-dimensional motion. I hope you remember that when you change direction, your velocity for that instant is 0. In the instant that you change direction, your velocity in that instant is 0. So for example, if you're changing your direction, your velocity can't be to the right because you're not moving right. And your velocity can't be to the left because you're not moving left, so the only thing left is that your velocity is 0. That means that you're not moving right or left or up or down, you're just changing direction. So in the instant that you change direction, your velocity is 0. Now that's still true for two-dimensional motion, but again we have to think about the components separately. You could be changing direction in one component and not changing direction in the other component. For example, you could be changing your vertical direction, but you might not be changing your horizontal direction. Or you could be changing your horizontal direction and not changing your vertical direction. So the new rule is, if you're changing direction in the x component, then your x velocity in that instant is 0. And if you're changing direction in the y component, then your y velocity for that instant is 0. If you're changing your x direction, then in that instant your x velocity is 0. But when you're changing your y direction, in that instant your y velocity is 0. We can actually see that on this graph that we drew. Is there any point on this path where the object is changing direction? Is this object ever changing direction? Well, it's never changing its horizontal direction. You can see this is never changing its horizontal direction. Over here we're moving to the right, we're moving to the right, we're always moving to the right. This object is always moving right, but the object does change its vertical direction. On the left-hand side, the object is moving down, but on the right-hand side, the object is moving up. So we do change our vertical direction. We change from going down to going up. Where's the point where we changed our vertical direction? Well, this is the point, right? At the very bottom of the path. This point at the bottom of the path, you can see that at this point we're changing our vertical direction. A little bit to the left here, we were moving down. And a little bit to the right, we're moving up. So here's where we're changing our vertical direction. So what would you predict about the vertical velocity at this point? When we're changing our vertical direction, what do you predict about the vertical velocity? Well, when you're changing your vertical direction, you would predict that your vertical velocity should be 0, right? So we would have predicted that when we're changing our direction, our y velocity should be 0, but that's what we already saw, right? We already saw that the vertical velocity was 0 here just by drawing the velocity vector. So this gives us some confirmation that we were right all along when we said when you change direction, your velocity in that component is 0. If you change your y direction, then your y velocity must be 0. You can see that right here. That was a consequence of the fact that the velocity vector is tangent to the path. So here, at this point at the bottom of the path is where we changed our direction. And you can see that the tangent here is just horizontal. When you're changing direction here, when you're changing your vertical direction, the tangent has to be horizontal. When you're changing your vertical direction, the tangent has to be horizontal. And you can see that this tangent does not have a y component. So that confirms what we've already been saying. When you're changing your vertical direction, your vertical velocity is 0. And we could also have drawn a picture that showed that when you change your horizontal direction, your horizontal velocity is 0. Here's the path of an object that's changing its horizontal direction. So where is it changing its horizontal direction? This is the point that it's changing its horizontal direction at. Well, let's draw the velocity vector. The tangent here looks like this. Here's the tangent. Well, you can see this is all y component. I'm trying to draw this as line as straight up. Here, the overall velocity is just the y component. There is no horizontal component. You can see that the tangent doesn't have a horizontal component. That confirms what we just said. When you change your x direction, your x velocity is 0. And when you change your y direction, your y velocity is 0. That's an important problem-solving technique. We've already seen how it can be useful for solving kinematics problems to know that when you change direction, your velocity is 0 in that component. Okay, so we've gone over some important ideas about the relationship between velocity and acceleration for two-dimensional motion. The most important thing we've seen is that we can't work with the overall velocity, and we can't work with the overall acceleration. Instead, we have to break the overall velocity and the overall acceleration into their components. Usually we'll work with an x and a y, a horizontal and a vertical component. And then once we've broken them into components, we think about the two components separately. And then we can use a lot of the skills that we've already learned for one-dimensional motion. We've also seen that the overall velocity is tangent to your path. We've gone over some very important ideas now about the relationship between velocity and acceleration, ideas that are important not just for kinematics, but for your whole physics course. So before you proceed, I'm hoping that you're going to just redo this previous section of the videos. Keep redoing this section until what we've gone over is boringly easy and obvious to you. This is material that is not good enough to know. This material has to be boringly easy and obvious to you, because you're going to be constantly building on this material throughout the rest of your physics course. So please don't proceed until you've really mastered the material that we've just talked about.